Revati, and thank you, Peter, for that insightful and informative talk about perovskite solar cells. I'm pretty sure our audience had a great time learning about the different aspects of perovskite solar cells. So, without further ado, I can see a lot of questions coming in our way. So, I will take the first question for you. Um, a pretty interesting one. How does modification such as change of metal cation or introducing different ammonium ions affect the morphology, stability, and overall performance of perovskite thin films?
Okay, yeah, thank you very much. That's of course an excellent question and a super broad question. It impacts, of course, everything. And yeah, I mean, I cannot go into very details, but with an optimization, what is typically done is to get a record efficiency with the right mix of these anions and cations. Unfortunately, the best performing solar cells are also the most unstable ones, and they suffer a lot, in particular from, let's say, demixing. And this is typically coming from inner stress, which is built up if these anions and cations are not having a good match in the radius. You have seen they are on this ABX3 crystal lattice, and there's a certain space. If the space is too much violated, then you build in too much inner strain into your system, which need to be released. And this is typically happening during operation and then causing degradation. So therefore, there's perhaps tricks to go beyond the so far used anions and cations. That would be perhaps an exciting route to explore. And with our scattering methods, we can always tell what is going on then on the detailed level.
Thank you so much for the response. Moving to the next question, one of our attendees would like to know how does the use of deuterium oxide specifically help in understanding the moisture diffusion mechanism in the methyl ammonium lead iodide thin films compared to normal water?
Yes, that's also a very good question. And yeah, so as I said, so D2O deuterium is an isotope to H2O, which means it has a different scattering length. So we see it differently in the scattering. You can think about in colors that, I mean, we have something what you want to see. And if you have white on white, you cannot see it. And if you have light gray on white, you see it slightly. And if you go to black on white, you see it very nicely. So a very high contrast. So with the D2O, what we do is that we enhance the contrast. So we go to something like black on white, whereas with normal H2O, we would be like gray on white. So we still see it, but not that good. And if we see things better, we can get a higher time resolution, and therefore we can follow the moisture ingression faster. So this is why we have used the D2O, and this is the strength of the neutrons. As I said briefly, X-rays have not this isotope contrast, and therefore they cannot differentiate between H2O and D2O.
All right. Moving to the next one. If perovskite solar cells degrade more in a vacuum compared to a nitrogen atmosphere, should they be explored for space-based applications?
Yes, perfect question. Exactly. This is one of the stressors in space. Yeah, so space means vacuum, and you're absolutely right. In space, of course, the vacuum conditions cannot be avoided. So the let's say answer is to use them in space, not to use mixed perovskites, because the mixed perovskites, they will undergo exactly this, let's say, demixing and phase segregation, and they will form what we have observed. But if we go into perhaps pure perovskite phases, this is not happening. So the take-home message is that there's two different branches. If you optimize solar cells for terrestrials, so Earth applications, that will be a different need to you optimize them for space. So for space, other material combinations of this fascinating perovskite family will be beneficial than on Earth. So simply sending the best ones to space, this is what we did in our first test. This shows limits, and this will not be what will be used in the end for space solar cells.
All right. Another participant would like to know what are some of the biggest barriers in terms of scaling these perovskite solar cells from laboratory level efficiency to reliable long-term industrial deployment, particularly in terms of, let's say, stability, manufacturing cost, environmental impact, and if you could share some insights on some promising solutions or strategies that could be implemented to overcome these challenges.
Yes, also a very excellent and broad question. So, I mean, what I did not touch too much, but you might be aware when you work in the field that there is a big success in commercialization going on in China, meanwhile, where companies really have successfully printed big modules and go to the market with big modules. And there's like a now a big move, which tells you that printing is the key to make these solar cells. And yeah, printing can be done and can be optimized that you really can come to a product. Of course, stability will be then an issue, and another issue might be the use of the lead, yeah, because lead is toxic, and whether we want lead in a big amount in our environment is a question which might have different answers in different countries. So therefore, perhaps for speaking for Germany, we might be concerned with a lot of lead in solar cells in our environment, and therefore also a big research branch is so-called lead-free solar cells in perovskite, where the lead is replaced by something else with the hope to, let's say, get lead-free in the end. Unfortunately, at the moment, they are not that good. Therefore, all, let's say, commercialization at the moment is, to my knowledge, really looking into the lead-containing ones. But I think we are in a transition. We are in a transition area where this is now really taking off, and you will see them, you will get them, you will be able to buy them. And perhaps in a talk in a year or so, we will talk about no more the question of whether this is commercialized or not, but perhaps how to make it more successful.
Amazing. Great to know that. Moving ahead, another participant would like to know what are the effects of skipping the use of an anti-solvent in one-step perovskite synthesis?
Yeah, I mean, this is of course one, I would say, really key things because the anti-solvent is, you have seen in the spin coating example I shared in great detail, something which is used to dissolve the originally formed perovskite. So you want to get rid what you formed originally. And in the spin coating, this is needed because spin coating is such a fast process that everything is kinetically controlled. If you go to printing, things can be slowed down and can be, let's say, not that fast anymore, that you have a better control, and therefore you can grow the initial perovskite already that good that the anti-solvent is no more needed.
All right. Another question is related to the GIVAX thing, which you talked about. So one of our attendees would like to know what are some of the spectral signatures in that technique that helps to indicate solvent complex phases. Uh, Example, lead iodide, DMSO intermediates. Uh,
So the point is, in dry wax, what you primarily see is if you have a crystalline structure, you get sharp Bragg peaks. If you have something like complexes, you get wide Bragg peaks. You can still analyze them and their position. Of course, you always have a signal in reciprocal space, so you need to somehow identify what it is really with the help of additional control experiments. The big strength is that in GIVAX you get the orientation, what I touched briefly with edge on or face on. You can think about this is your electrode, and the question is whether it's stacked this way, like a sheet of paper, or whether it's stacked this way, like a books in a shelf. Yeah, and this matters a lot in terms of how charges are transported.
okay. I think a lot many questions are still coming in our way. I can take one more. It's related to GIVAX only. It is very difficult to see any change in GIVAX for ultra-thin passivation layer if they do not form any two-dimensional structures. So can techniques like XRR or Unida scattering be useful to characterize these ultra-thin passivation layers?
It's again a very perfect question, and I would partly disagree. You can see with GIVAX also their structure information if you use the right critical angle or if you come from the other side. Yeah, so if you irradiate from the other side, so not from the standard side. But of course, with reflectivity, you would get information about the homogeneity of the layer and the thickness of the layer and the roughness of the layer. Yeah, and this Unida scattering gives you also information about like the yeah, homogeneity of the layer. So this is also all techniques which will give you additional information.
Okay. Uh, I think one more question is one of our attendees would like to know if you could please share your perspective on the use of halide perovskites for MEM resistors.
Okay, for memristor, I mean, I didn't touch that. Yeah, I had one slide. I skipped for time reasons to go beyond the solar cells. And actually, this is what is happening. So perovskite is explored now more and more in other areas. Yeah, so they start to go into light emitting diodes. They go into memristors. They go in all type of electronic devices. You see them as photodetectors. So I think they appear everywhere. And it always follows the same scheme that they have, on the one hand, this very high tunability. So you have this super big, let's say, landscape of anions and cations you can let's somehow explore, and thereby you can tailor so easily band gap and structure and all these things. And on the other hand, they are so easy to process and to manufacture. And that means they open really always route to commercialization. So it's not a very tedious high vacuum MBE process, which is very expensive, needs very delicate equipment. Yeah, you can really very easily go into upscaling commercialization. And this is for all electronic applications always interesting.
All right. I think in the interest of time, we can take just one more question, if that's okay. So does the perovskite solar cell needs encapsulation of the type that we are using for silicon cells right now, or the encapsulation methods would be relatively cheaper in this case?
I mean, the point is, of course, in the end, you will need to encapsulate them if you want long-living solar cells, and the encapsulation need to be optimized for the perovskite. Yeah, so to simply copy the encapsulation from the silicon world is a too simple, let's say, approach. And there is groups in the world which are experts in this encapsulation. Yeah, and typically the challenge is not encapsulation from the top. The challenge is the edges in the encapsulation of the solar cell. But if you check out, there's really a big amount of literature of such optimized encapsulation processes for perovskite solar cells.
All right. Great to know that. I think we are closing in towards our time. So before wrapping the session, Peter, if you have any closing remarks for our audience today.
Yes, as a closing remark, on the one hand, like to remind you that ACS AMI is a fantastic journal if you have a similar research direction, and we will be happy to take your work into consideration. On the other side, I like to thank you all for joining from all around the world. Yeah, I heard that you come from really all different areas and all different time zones, and perhaps not from such a convenient time zone like Germany, because we have early afternoon. You might have early morning or late night. And this is really, I'm very thankful that you join. And as a last word, I mean, we are fascinated by perovskites. It's an amazing material. It has so many chances. And I hope I can share this fascination, and perhaps you will also do this research in your future. Thank you.